Hello everyone and welcome back. Today we are going to solve this question. A projectile is launched with a velocity u at an angle theta, but however it is going to bounce and some energy is lost because it's an inelastic collision, and it keeps on bouncing until all energy is lost. So we should find the final displacement of the projectile. Let us see. So looking at it, let's make an image. Let's make an image on how things would look. So this is my y-axis, this is my x-axis. So I launch it with a velocity u like this at an angle theta. So the trajectory of this will be a parabola, and now this bounces again. So this is going to be a smaller parabola because some energy is lost, and subsequently the parabola's peak keeps decreasing and until it just becomes 0. So what we are asked to find is this total distance it travels. Let us see how we can approach that. So what I plan to do is so let us start off by finding out the time period. So let this one have t1, let this be t2, t3 and so on. So we know that time period of a projectile is given by, time of flight is given by 2u sine theta by g. This u sine theta, let me write it as the vertical component of the velocity. You will see soon why we are doing it. 2uy by g. This is the general time period of a projectile. So we have t1 is equal to 2uy by g. Now after t1 the projectile reaches this area, and let us look at that collision carefully. So this is the floor, and we know that it's going to hit back at the same velocity it was launched in at the same angle, but just going downwards. So resolving this velocity into components, we get let me do it in a different color. We get u sine theta downwards and the u cos theta towards the right. That remains unchanged. Now let us apply the rules of collision to this collision. Now what do we get? We know that the coefficient of restitution from the floor is e, and we know that the velocity changes only normal to the surface of collision. So this u cos theta which we have will remain unchanged. Only the vertical component of the velocity will change. How will it change? So we know that after collision the new vertical velocity is going to be, velocity of rebound is going to be e times the incoming velocity, that which is going to be e u sine theta. So like this. Now this it rebounds back upwards with eu sine theta, but its horizontal velocity remains constant, u cos theta. Now let us focus on this point after t2. So let us find t2. T2 is going, now the vertical component of this velocity is eu sine theta. So t2 is going to be 2 eu sine theta by g. Similarly, after t2 in this collision, it will rebound again vertically with a vertical velocity of e square u sine theta, and its horizontal component will remain unchanged, u cos theta I cap, and so on. After every collision, we can see that its vertical component of the velocity is getting multiplied with e, but the horizontal component is remaining the same. So let us try to find the total time. So t1 plus t2 plus t3 up to tn, it's going to be 2u sine theta by g plus 2 eu sine theta by g plus 2e square u sine theta by g, and so on. So let us factor out 2u sine theta by g from the entire term. So let us represent this total time with capital T. T equal to 2u sine theta by g times 1 plus e square plus e cube, and so on up to infinity. Yeah. Now how do we solve this? We know that E is always less than or equal to 1, and in this case, as this collision is inelastic, we can say that E in this case is less than 1. So this series is a converging series. We can apply the formula. So the formula for summation of infinite terms of a converging series is given by A by 1 minus R as infinity equal to A by 1 minus R. Here, as we can see, A equal to 1, and what is the common ratio? Each term is getting multiplied with E, so we can say R equal to E. So T is going to be 2u sine theta by g into summation infinity of times. So let me just, which is 2u sine theta by g times 1 by 1 minus e. This is what we get. This is the total time taken. This is the total time the projectile will keep on traveling, keep on bouncing. But how do we find the range? We just know the time now. Now let us go back and let us go back to one of the observations we made. So what did we observe? We observed that only the vertical component of the velocity is changing. The horizontal component, on the other hand, is u cos theta. Horizontal component has been, and it is always u cos theta throughout the whole journey, u cos theta. So we can find the horizontal range by multiplying the time taken into its horizontal velocity, as it's constant throughout the journey. Now let us do it. So total displacement is given by u cos theta, that is the horizontal velocity, into 2u sine theta by g into 1 minus e. This is what we got. So we get d equal to 2u square sine theta cos theta by g into 1 minus e. We know that 2 sine theta cos theta can be replaced by sine 2 theta. So we get d equal to u square sine 2 theta by g into 1 minus e. So yeah, some keen observers might notice that this part of the formula, it is the range of a projectile, but only it is the range of projectile which comes to rest after one collision. It doesn't bounce. So yeah, that is a keen observation. So finally we can say that its displacement is given by u square sine 2 theta by g into 1 minus e. This is a pretty universal formula. Even if the projectile doesn't bounce, this can technically be applied. So what does it mean the projectile doesn't bounce? It means that it is a perfectly inelastic collision. So what is the value of E for the perfectly inelastic collision? E equal to 0 for perfectly inelastic. So putting E equal to 0 in the formula, we get d equal to u square sine 2 theta by g, which matches. We already know that this is the range of a projectile which doesn't bounce, which comes to rest after one collision. So this is a pretty universal formula which can be used in any case. And we are done for the video.